Hey you, it's me. Let's talk about modified binary search. If you're new to binary search or just want a quick refresher, then I suggest you checking out my video on vanilla binary search. You can think of modified binary search as regular binary search, but in certain cases we might not discard the entire half of an array, or the underlying array that we're searching through is not sorted how you would assume it is. So it might require us to identify new boundaries or to introduce new conditions to help us navigate to the element that we're searching for. For today's example, we want to find the smallest element in a rotated array.
What the heck is a rotated array?
We can rotate an array by taking an array that's sorted in ascending order, we pick an arbitrary point within the array, and then we take all the elements that are to the right of that point and move them to the start of the array. For an example, we have this sorted array. Let's say we pick the arbitrary index of 2. Now we move our elements 4, 5, 6 to the front and we'll get 4, 5, 6, 1, 2, 3. Something we should notice about this array is that it has a special property. You see here it has 2 sequences. The first sequence is filled with all the larger numbers in the array. The second sequence has all the smaller numbers. But before we jump right into figuring out how to use modified binary search, let's just assess what our other options would be for finding the smallest element in this rotated array. So our first option, we could just sort the array again in ascending order and then use binary search to find the smallest element. At best case, the time complexity would be sorting, O n log n, plus binary search, which is log n. We take the worst of those two complexities, which is O n log n, and that would be the time complexity to sort and then use binary search.
That's not optimal.
We could just search through the array in linear time, which is O n.
That's a little better.
But still nowhere as good as what a binary search can offer us in just log n time. So let's figure out how we can make binary search work for this rotated array. The first thing that we want to keep in mind about binary search is that it works over sorted sequences. And what does our example rotated array have to offer? 2 sorted sequences. We know that the minimum element in the array will, by default, fall within the second sequence. That means that all we really have to do is find where the first sequence ends or where the second sequence begins. To put it in other words, if we wanted to find the max or the min element within this rotated array, we would eventually land at index 2 or index 3 for element 6 or 1 respectively. So to get this going, we first want to create a left and a right boundary pointer. These will be created the way that we normally do in binary search. Then we want to create a while loop that keeps running as long as left doesn't equal right. And at each iteration, we find our midpoint using our left and right pointers. Now here's where things get a little tricky. If our midpoint falls inside of sequence 1, then our midpoint's value will be greater than the value at our right index. Because remember that the minimum element will fall in the second sequence. So if the value of our midpoint is indeed larger than the value of our right index, our strategy will be to update our left pointer. We will make it equal to our midpoint plus 1. Since we know that the current midpoint is in the first sequence with all the larger elements, we can exclude that from our new boundary. And now we want to look at our other case, where the value at the midpoint is equal to or less than the value at our right index. If this is the case, we're going to update our right pointer to be equal to our current midpoint. Now let's see this play out with the example above. Within our first iteration, num's index midpoint will be greater than num's index right. So we're going to update our left pointer. On this next iteration, it's actually going to be the other case. Num's index midpoint will be less than num's index right. So now we're going to move our right pointer. This next iteration will also have num's index midpoint less than num's index right. We update our right pointer, and look at that. Right and left are both pointing to the same element. And it's the smallest element in the array. So this would be our stopping condition for our while loop. Now that we've actually gotten to rotate an array and evaluate each conditional, it's time to put this to good use. Let's go to LeetCode, find a problem, and start solving. Today's problem is going to be 153 Find minimum in rotated sorted array. Suppose an array length n sorted in ascending order is rotated between 1 and n times. For example, the array nums 0, 1, 2, 4, 5, 6, 7 might become 4, 5, 6, 7, 0, 1, 2 if it was rotated 4 times. Given the sorted array nums of unique elements, return the minimum element of this array. You must write an algorithm that runs in O log n time. And lucky for us, that last sentence is a dead giveaway. They're expecting us to use binary search to solve this problem. We want to start off by defining our pointers. In normal binary search, we might call these low and high. But since the values of this array have been rotated, it's a better idea for us to call these left and right. That way it's easy to understand exactly what side of the array they're pointing to. Next is our while loop. We want to keep it going as long as our left pointer is less than our right pointer. You might notice that this boundary is unlike the normal binary search condition. Remember that in normal binary search, we want to stop when our left and right pointers actually cross each other. They're allowed to be pointing to the same element. In a rotated array, however, we don't want them to cross at all. We want to exit as soon as left and right are equal. So now we find our midpoint using this method that you might recall from my other binary search video. This just allows us to avoid integer overflow. Okay, so our first conditional within this while loop is going to check if num's index midpoint is greater than num's index right. If it is, then we know that our midpoint is pointing towards the first sequence in the array where all the numbers are larger than the second sequence. So if this is the case, we're going to update our left pointer to be equal to midpoint plus 1. We can disregard mid because we just evaluated it and know that it's definitely not the smallest element in the array. Our else statement means that num's index midpoint was equal to or less than num's index right. So because right was actually the bigger number in this case, we're going to update it to be equal to midpoint. We aren't excluding midpoint in this new boundary like we did in the previous conditional. And that's because it's actually a smaller element, so we want to hold on to it. And we leave left wherever it was because we're preserving that also as a pointer to a small element. And eventually what will happen by updating our right pointer in this conditional and our left pointer in the other conditional is that they're going to point to the same element, and that same element that they eventually point to will be the smallest in the array. So outside of our while loop, we're just going to return num's index left. And that's just because, as we said before, left was used as a placeholder for the smallest element in the array. And that was using modified binary search on a rotated array. I know that when I first saw problems using rotated arrays, I could not wrap my head around it. It was so difficult for me to reason about. But after I was able to visualize an array getting rotated and see the breakdown of each step when you're using modified binary search, it made so much more sense to me, and it became a much more approachable problem. And this is not an easy problem by any means. Actually, what we just solved on LeetCode is a medium. But I hope that you don't find this problem as intimidating anymore, especially now that we've broken it down into its components and actually visualized what it would take to sort through the array with our modified binary search. This was a challenging but rewarding problem to solve. Don't forget to like and subscribe, and don't be afraid to leave a comment if there's any patterns, algorithms, or problems on LeetCode that you want to go over. I'm so thankful that you took the time out of your day to come and study these problems with me. So from me to you, have a great day.
No, we can do better than that.
That's not good.
That's bad.